Okay. Some of these questions are from chapter 5 and 6 of your course reader. Okay. And then some of these questions require hand calculations, but you can use Mathematica as an aid, for example, to plot functions to check if the limit exists or not. Okay. So this time, let me ask you to do question 1. Question 1 first. Question 1 is about limit of sum of two sequences. Suppose you are given the sequence limit of an is a and limit of bn is b as n tends to infinity. Use the epsilon n definition of the limit of sequence to show that the limit of the sum is the sum of the limits. Okay. Can I ask, can someone tell me what is the definition of epsilon n for any sequence? In your assignment, instead of the sums, the product is given. Okay, so this is really an idea of how to get started with that. Can someone explain me what does it mean by if limit a n goes to infinity a n equals a using the epsilon n definition? Okay, thanks, Ashish. That's a very intuitive explanation. Small epsilon and large n, it should converge. Okay, within that epsilon neighborhood. Okay. So using that, can you guys start with question 1? Okay, let me explain this part. What does it mean by limit of a n tends to a as n increases? I need to stop share this. So this is the definition of limit of a sequence, convergent sequence. So if we let a and b from n equals 1 to infinity where sequence of real numbers, we say that the sequence has limit L, which is in real, if for every epsilon. Okay, for every epsilon you give me, there exists a positive integer n such that if any n greater than or equal to n, then the absolute value of like a n minus l is less than epsilon. Okay, so this just bounds a n for a small number. Okay, so if you want to, intuitively, this is an illustration of what's the going on in the definition. Let's say you have the sequence values is like this. This could be a positive or negative sequence of values, and which converges to limit a. So the epsilon n definition says, if you give me any epsilon, okay, this is epsilon distance, okay, then this tube, okay, where after if you give me any epsilon, I can choose an n, let's say n0. After that n0, the sequence is within that epsilon tube here. Okay, so regardless of which epsilon you choose, there is an index n such that an lies completely in that epsilon tube. Okay, that's the definition. So in this case, there is just 1 point outside that epsilon tube. But now if you give me another epsilon, which is smaller than E, the first epsilon, let's say that's epsilon 1, then I can still choose n. This time, let's say it's n1, where the sequence, the elements of the sequence are still bounded within this epsilon tube. Okay, so intuitively, that's the definition of epsilon n. Okay, is there any question? So however small the epsilon is, you can still choose a positive integer beyond that, like afterwards, the values of the sequence lies within a bounded region. Okay, that's the definition. Any question? No? Okay, how would you start with that question? Where you have use epsilon and definition to show that if limit n tends to infinity of a n is a, and b n is b, then the sum of the limits is the limit of the sums. Sorry, yeah. Okay. Let's start with the definition of this one. Okay. Since limit of a n is a, then we can say that there exists an n such that for every epsilon 1 bigger than 0, if n is bigger than that n1, that's n1, then a n minus a is absolute value of a n minus a is less than e epsilon 1. Okay, is everyone okay with that? Okay. Then from the second statement, similarly, since limit of bn is b, we can still say there exists an n2 such that for every epsilon 2, if n is bigger than or equal to n2, then we have this result here. Okay, so that's by definition of the limit. Now, now we want to show that limit n tends to infinity, an plus bn is equal to a plus b. So using this definition, instead of an, you would replace that by an plus bn, and then this is the sum of the limits. Okay, now start with that. Okay, what's the next step? How would you split that into two absolute values? Anyone? Yeah, you're close. Yeah, trough. Yeah, it would be less than I1 my epsilon 1 minus. Is it minus? I should say is less than sum of each term of A and B. Okay, triplet says plus. Yeah, some of you are close enough. So the second step is using the triangle inequality. We can go from here to here. Okay. Then because an minus a is like we have defined it here, we can use that as less than epsilon 1 plus epsilon 2. But remember, we want something like this. We want an plus bn minus a plus b uh, less than epsilon for some n. Okay. Um, for all n bigger than or equal to some n. Okay. How do we choose that? How do we choose this epsilon and how do we choose this n? Anyone? Some E1 and E2, yeah. But can you really choose E1 and E2 so that the sum is the epsilon? Ashish? It will be for large N. How large? Like what is that capital N that you need to choose? Can you relate that to the previous? Can you relate this N to N1 and N2? Triplet bigger than N1 plus N2. Yeah, that's a good triplet. Thanks, triplet. It's good. Sum of N1 and N2. How about, okay, some of you are close. Let's say, okay, you can take N to be bigger than or equal to N1 and N2, but what exactly is that? Remember, I want finally E here. Okay, how would you choose E1 and E2? Epsilon 1 and epsilon 2. I remember when I did this question in undergrad, my professor just say or choose this one. Like he started with choosing the E1, epsilon 1 and epsilon 2. Then I was like, how do we choose that? So that's where I am trying to get you up to. Okay. Okay, so we can choose epsilon 1. And so initially we go up to this step, but then we go back again um, and say that we can choose epsilon 1 plus epsilon 2 to be less than or equal to um, epsilon. Example, if I choose epsilon 1 and epsilon 2 to be epsilon over 2, would that help? Okay. If I choose epsilon 1 and epsilon 2 is this one. This is just one choice. Okay. Um, there could be others. And choose n to be the maximum of n1 and n2. Why do we do this? We do this since if n1 is less than n2, then for all small n bigger than or equal to that n1, we have this case. But if it's the other way around, we have that case. So we really need it to be maximum. Okay. Therefore, from here, we can say that we could go back and say, let's E1 be equal to epsilon over 2. Let E2 be epsilon over 2. Then we come back here and say um, this is equal to epsilon over 2 plus epsilon over 2, which is equal to epsilon. Okay, and provided that we choose n is maximum of n1 and n2. Okay. All right. Something similar can be done for the product of the limit of the products as well. Okay. Is there any question? Is this clear enough? Is there any question? Tripod says yes. Yes means there is a question. All right. Okay, I got it. Thanks. Let's move on to the second question. Let me check the second question. Derivative of sin x. This is interesting. Okay, there is a question which says, remember this statement, trove. what is not clear. So whether they prove the sum of limit is limit of sums. Okay. From all that we have done, we have come up to this step. Okay. This shows that for any epsilon, okay, positive, there exists n which is equal to maximum of n1, n2, such that we have an plus bn minus a plus b less than epsilon, okay, which implies limit n tends to infinity of an plus bn is equal to a plus b. Okay. Is that clear? Trov, did I clarify your question? Okay, good. Let's move on to the second question. Second question asks about, give a geometric explanation of why the derivative of sin x equals cos x. I'd like to show the notebook. Geometric explanation can be a plot, and using the plot you can explain it. Okay, let's plot sin x and cos x on the same diagram, same image. We have plot on both functions. So and we need to give plot range. Let's say let's start with x minus 3 to 3. Okay, legend. I think I've done this. Plot legends. Yeah. Okay, so that's a plot of sin x and cos x. Okay, can you tell me why the derivative of sine x is cos x? By the way, what's the definition of derivative? What's like in English words, what's the definition of like derivatives? How do you calculate it? At a point, derivative at a point. Anyone? Slope, yep, yep. Yeah, how a function varies, good. Yep, true, that's exactly what we are looking for. Our limit is h goes to 0. The function at x plus h minus function h at x divided by h. Okay, good. But intuitively, using this geometric plot, how do you show that the derivative of sine x is cos x? Okay, take some points on sine x. Okay, if I say x is 0, what do you think is the derivative of sine x? No, we don't want, this question asks you show geometrically. Okay, so we do not want to calculate it. I just plotted this so that you could compare the two functions. Okay, so at x equals 0, what's the derivative of sine x? Not trigonometry, but just look at the graph. If you would compute the derivative, you would draw a tangent line, right? At that point. Okay, let's say, imagine you are drawing a tangent line at this point. What would be the slope of that tangent line? 1, good. Okay, so the derivative of sine x is 1, so you go up there and then put a point on top. Okay, let's come back to yeah, this point up here. Okay, at this point, what's the derivative? 0, very good. So we go and put a point here. Yeah, parallel to x, so the derivative is 0. And so that's a point up there. And then we come back to this point here. What's the derivative at this point? 0 as well. So we go up and put a point up there. So that's intuitively in geometric sense that how you could explain it, okay, without using a formula or trigonometric identities. We could see that, let me stop share. Let me share my screen again. Okay, my graph may not be accurate, but this is a little bit explanation that I can give. So this is sine x, okay, and let's say it looks like the derivative here, like is here. So if I put a point here, look at the slope. The derivative looks like 1. So put a point there and then come back to this point. The derivative is parallel to x-axis, so it's 0. Put a point here. And this one, again, the slope is negative. It looks like a -1. So this is another point. And take a point here. This is the tangent, slope of the tangent is 0 again here. So something similar you could do. So you could see that when you join these points, okay, looks like it's tracing the cosine curve. Okay. Is that clear? All right. That's a good question, Tro. A geometric interpretation of how we can prove it. Well, this is, I think we need to use, what do you mean by a circle? I'm not sure about that. True. Yeah, you can prove using another method, but I was trying to address the question, a geometric interpretation. You might want to use something else, which is fine. Okay. All right, the second part is prove the result in part A using the fact that sine x plus h equals sine x. That is the trigonometric identity. Okay. Right. I started with the geometric interpretation of the derivatives of a continuous function. So some of you have already told me what this is. So the derivative would be the slope of the tangent line here, which you would use as the rise, like rise over run formula. Okay. So this is the formula that you need. Okay, so I've started this with if you can apply this formula here. Okay, f dash at a point. Okay, now can you use the hints given in the question to progress? I've given a hint saying like you can use trigonometric identity to write this down. Yep, Ashish says expand sign of x plus h and apply limits. Yes, that's exactly what you need to do. Um, that's the second step. Now you can collect all the sign terms. All right. And if you go through this step, okay, you can either compute this limit by like calculate it by hand, or you can use Mathematica to draw the line or compute the limit using the limit function. Okay, is everyone okay with that part? So after this step, what I did was like this is like factorize sin x from here. And in this step, the limit is on h. So cos x is a constant term here, and sin x here is a constant. Then you have to take limit of sin h divide by h as h goes to 0. Okay. I've drawn a graph which I plotted in Mathematica. You can use the plot function to visualize this. Okay. And we see that as h tends to as x tends, like in this case, or you can replace this by h. As h tends to 0, the limit is 1 here, and it tends to 0, the limit is 0 here. Okay, and then applying that, we get the derivative of sin x is cos x. All right. Any questions? Okay. Next question is question 3, product rule, chain rule, quotient rule. Using only the product rule and the fact that dx by dx is 1, calculate the derivative of x cubed. Okay, that's the first part. Second part is prove the quotient rule for the derivatives using the chain rule, product rule, power rule. Okay, can someone tell me what is the product rule? I didn't show the question. I'm assuming that you have the notebook with you. What's the product rule? Um, anyone? Yep, Trop, that's good. What's the quotient rule? Product rule is like fx times gx derived, you take the derivative of the first function. Yeah. So in your notation, you've said this is u, this is v. Yeah, this is u dash v and u v dash. Yeah. Yep, that's the quotient rule. What's the chain rule? Yeah, chain rule is, yeah, if you have one function in terms of the other function, you can use the chain rule to get the derivative. So that means, so you derive the actual function, multiply the derivative of the function inside of it. Okay, and what's the power rule? I think I've given you. Okay, power rule is x to the power n, that when you derive it, it's n times x to the power n minus 1. Now, first part is use the product rule to calculate x cube. How would you use that? Anyone? Can you write? Yeah, yeah, Ashish is right. Apply x squared times x. Yeah. Use the product rule first to get compute d by dx of x cube is equal to d by dx of x times x squared. Now you can use the product rule for that. Okay. And then once you have done that, you can still, yeah. And then again, you use the product rule again for x squared. Does that make sense? Okay, yep, we are running out time. Let me share what I did. Okay, part B is proof quotient rule. Okay, remember quotient rule is this one. Okay. We need to prove that. How do we do that? Using only the product rule, chain rule, power rule. Yeah, use chain rule first on what? Yeah, would you use chain rule first or would you use the product rule first? Um, Okay, how would you use chain rule first? Okay, good. You could, okay, this is how I started with that. Let me define hx as fx over gx. Then I can write, yeah, that's good, Trove. Then I can write this as fx times gx to the power -1. Then use the product rule first. Okay. So the first step is using the product rule. And then, oh, this is my shorthand rotation. I started with d by dx, but then converted to like f dash h dash. So don't worry about it. The next step is using the power rule and the chain rule. So this is f dash x, and to get this, the derivative of this g to the power -1, I use the chain rule and the power rule. Now, once you go up to this step, you can use, this is to the power -1 is really divided by gx. And here also to the power -2 is divided by gx squared. Rearranging this and then making common denominator, you would be getting the product rule. Sorry, this is the quotient rule. Okay, is that clear? Any questions so far? By the way, I have the codes with me. I will update the codes on GitHub. Please have a look at it. Okay, I am running out of time. I've got another class in 5 to 10 minutes. So I will have to leave by now. Let me go through. The next question is, question 4 is about evaluation of a series and approximation, which will be helpful for your assignment. Like all of these are helpful for your assignment. I just need to explain the code. Okay, and harmonic series. Question 6 is optimization, which should be easy for you guys. And taking the limits. Question 7, you can use the limit function in Mathematica. Okay, limit function in Mathematica for question 7. To see what is the limit, and then you can compute it by hand. Okay. All right. Let me say, meet you next week. Okay.